Alright, so today we're going to have a look at disproofs, examples, and counter-examples. So there are many different ways that we can disprove a statement depending on whether this applies to all numbers and that would be our for all symbol, or to at least one number, and that's our there exists symbol. So the easiest and one of my favorite ways to disprove a universal statement is just by providing a counter-example. So if we've got some sort of statement and we said for all integers n that they're odd, well, we know that's not true, and you only need to provide one example to disprove that whole statement, because the for all symbol means every single real number. A few other ways we can disprove these universal statements: we can use our direct proofs, we can use contradiction, and we can use proof by cases for proof for false for at least one case. That's really just the same as that first thing there. Okay, we've got to prove that the following statement is false. If a squared minus b squared is greater than 0, where a and b are real, then a minus b is greater than 0. Okay, now this is a universal statement because we're saying this whole statement is always greater than 0. We're not saying if a is equal to 3 and b is equal to 1, then it's greater than 0. We're saying a and b are real. It's always true. So we just need to provide one counter example. So I reckon if a is, minus 2 and b is 0, then we know that minus 2 squared minus 0 is equal to 4 minus 0, which is greater than 0. However, minus 2 minus 0 is less than 0, so therefore false. So the way of disproving a statement, if it's a universal statement such as this one, is just by providing one simple counter-example, and that throws the whole universal statement out the window because it's no longer universal, it might just be existential. So example 2, where you're going to disprove the statement that there are no prime numbers divisible by 5. Well, 5 is prime and divisible by 5. Therefore, the statement is false. Okay, disproving equivalent statements. So we've got to disprove a statement that applies to just one real number. We can't use a counterexample, as it's perfectly acceptable that there are many numbers for which the statement is false, and yet there could be a few numbers to show that it's true. So we can use a direct proof to show that the negation of the statement is true for all values, so the original statement is false for all values. Or we could use a direct proof to get with a contradiction. Okay, so here we've got the statement that there exists a real number x such that x squared plus 2x plus 5 is less than 0. So again, my favourite out of these three is this one here. So we're going to prove that the statement is false for all real numbers. So let's suppose that we might suppose that this statement is equal to a, so let's suppose that it's greater than 0. Well, the discriminant of that quadratic expression is equal to 2 squared minus 4 times 1 times 5, and that's less than 0. So if we've got a being greater than 0, and what I meant by a, I meant a is this number here, which is a 1. So this is a happy parabola, it's an upward facing parabola, but our discriminant is less than 0. So if you've got a parabola that's facing up and a discriminant that's less than 0, that means it has no x-intercepts. But if it has no x-intercepts and it's an upwards facing parabola, then it can't ever be less than 0. So this quadratic is always positive. Therefore, the statement is always false. Okay, we're going to prove that this statement is false. There is a Pythagorean triad where all numbers are odd. This particular example, I think it would be best to do by contradiction. So we're going to assume that there is a Pythagorean triad where all numbers are odd. So let's say we've got the Pythagorean triad. A is equal to 2i plus 1. B is 2j plus 1. And C is 2k plus 1. Well, Pythagoras' theorem states that c squared is equal to a squared plus b squared. So let's have a look at this. We've got 2k plus 1 squared. I might say as well, since we're trying to contradict something, we might come up with an assumption. Let's assume there is such triad. Is equal to 2, what did we say A was? 2i plus 1 plus 2j plus 1 squared. If we expand all of that, we're going to get 4k squared plus 4k plus 1. And if we expand the right hand side and factorize, we're going to get 4i squared plus I plus j squared plus j plus 1. And we expand the left hand side, we're going to get 4 k squared plus k. We can kill those ones there, they die, is equal to 4. Actually, those ones don't die. Sorry. What happens to the ones? Oh no, I've missed a 1, sorry. 4k squared plus... I missed a 1 somewhere. There is another 1. No, this is not here. Okay, squared plus k plus 1. Let me just start that again. Okay, if we expand all of this, we're going to get, I think I did too many steps in one there, 4k squared plus 4k plus 1 is equal to 4i squared plus 4i plus 1 plus 4j squared plus 4j plus 1. We can, first of all, we can kill one of the ones there we go, and this is going to equal 4k squared plus k is equal to 4i squared plus I plus j squared plus j plus 1. And the plus 1 should be at, we can't factorize out that 1, that has to be there. However, k, j, and I are integers. Let k squared plus k, we might say it's equal to the integer m, and I plus I squared plus I plus j squared plus j, we might say let it equal to n. So 4m is equal to 4n plus 1. Right. That is not possible to have integers, a Pythagorean triad, this is not possible because we're saying that this is equal to this, but this is a multiple of 4 and this is not a multiple of 4, so they can never be equal to each other if we're talking about integers. So the left-hand side is a multiple of 4, but the right-hand side is not. So they can't be equal to each other. We can't have a multiple of 4 that's not equal to a multiple of 4. That doesn't make any sense. So, therefore, the statement is false. And that's because this is a contradiction. It's a contradiction to the statement c squared is a squared plus b squared, because the left-hand side has to equal the right-hand side, but you can't have a multiple of 4 that's not equal to a multiple of 4. That doesn't make sense. It's a contradiction. So therefore, such a Pythagorean triad does not exist. Okay. We're going to prove or disprove that the statement is false. So we're going to prove or disprove that the sum of the squares of two consecutive numbers is divisible by consecutive even numbers is divisible by 8. So let the numbers, first of all, an even number, and the consecutive even number directly after it would have to be 2k plus 2. Okay, and that's for some integer k. We're going to sum the squares, that's what we're asked to do, 2k squared plus 2k plus 2 squared. If we do that and expand that, we're going to get 8k squared plus 8k plus 4, which is equal to 4 2k squared plus 2k plus 1. Now, that's not divisible by 8, which is not. So therefore the statement is false. And last question for this video, we're going to prove or disprove this statement here. There exists a real number n such that 3 to the power of n plus 4 to the power of n is equal to 5 to the power of n. Now I'm thinking, oh, that looks like a Pythagorean triad. And this is not a for all, this is a there exists as an existential quantifier. So I only need to show that one example is true. So let n equal 2. We know that 3 squared plus 4 squared is equal to 5 squared. That's true. Therefore, the statement is true. Now this is a rare example where one statement proves the whole statement, and it's only true because we've got this symbol here and not a for all. Awesome, and that is proof by, what was it, logical equivalence, I think. Thank you.